Our graphic syllabus from the beginning kind of laid out the whole semester, and I think it would be good to take a look at where we are now. Maybe at the end of each chapter we'll take a look. But so far we've done chapters 10 and 12 and 13, so we've kind of conquered this idea of vector functions and the velocity and acceleration and motion. And so we've hit the vector functions, we've studied the vector functions. We can take derivatives of vector functions and take integrals and apply it to parametric equations. And it doesn't say here, but we also were able to apply some calculus to polar coordinates. And we didn't apply calculus to conic sections, but we know the graphs of conic sections and even the three-dimensional conic sections, which are quadric sections. Actually, they're called more surfaces. And so we've studied all that so far, and now we're ready to get into this idea of studying multivariable calculus. So the next test that we'll have will encompass the multivariable functions and taking a look at their derivatives and integrals. And so we'll start by looking at them, studying them like we studied our functions y equals f of x back in pre-calculus. We'll take a look at them from numerical, graphical, and symbolic points of views. And then once we are comfortable with looking at the shapes and the graphs and some ideas about how these functions might look like, if we can visualize them, then we'll be ready to take derivatives and integrals of them. So the derivatives will come in the same chapter, and then the integrals will come in the next chapter, and after that we'll be ready to take our second midterm. Okay? That is our layout. So today we'll get introduced to functions of several variables. We'll take a look at the notation that that I'm going to want us to use, and then we'll take a look at some examples as well. And I think it would be good to establish some notation early on, so that when I start writing these weird things up on the board, you'll know what it is I'm talking about. So we'll go with the definition of a function of two variables for starters. And the function, I mean, the definition might look a little complicated, but let's see if we can parse through the sentences here. A function of two variables is a rule that assigns to each ordered pair a unique real number denoted by f of whatever that ordered pair is. The domain of f and its range are a set of values that take on, the set D is a domain of f, where D is some ordered pair of real numbers, and the output is the range is a set of real numbers. So I want to assign a special notation for this that we may or may have seen before, and I wanted to write it out because I'm going to continually make analogies or relations with some functions that we've known in the past. So this notation says that f is the name of your function. The colon says, okay, we're going to be ready to describe the domain and the range. So the domain is going to be a set of ordered pairs of real numbers. And we use these two bars on the R for representing the set of real numbers. And then the 2 over here says that you're looking at a pair of numbers. So when I teach algebra and those lower level classes, and they see the x and then the 2 as a superscript number that's higher, and they say x2 when it should have been x squared or x to the second power. But this is, we don't call it to the second power. We're not squaring. We're not algebraically squaring the set of real numbers. We're kind of doubling it. So we say R2 for this, not R squared. So we're going to pull it back and say R2. So what? Colon says that what's going to come next is going to describe the set of domains in the range. And then the domain is the set before the arrow, and the range is the set that comes after the arrow. We'll call it, so the range and codomain, or even image, some people call it image, they're all kind of semi-interchangeable. And when I say range, I just mean this is the set where you can get the image from, the codomain from. So codomain would be the exact set of values of what the range usually is. So let's be, I don't want to say careless, but let's be a little loose on the term range and codomain and image, because we'll say, when I say the range, I mean this could be a possible set of real numbers, but if we want to, the range, how it's defined in the book, they mean the actual set of values that it's going to hit. So you guys can figure that out later. And sometimes we can add on more specifically here, or sometimes I put it down here, depending on where I am. And what I can describe now is a specific set of values, or an example set of values, where the R2 actually means an ordered pair of numbers. And we can look at it as a point, or we can look at it as a vector. So this is where I want you to be kind of flexible as well. And this time the arrow has a little line in the front here to say, okay, this is specifically what's going on. And your output is going to be the output that you get, the real number value that you get when you put in the ordered pair of values. So this is another way to describe what we're talking about. Just to make an analogy from back in pre-calculus, where you have y equals f of x, for example, just a random function. The way this notation would work is that the name of my function is f, so I'll call it f:, and the domain where I get this from, or the place where I'm going to get the domain from is just a set of real numbers. And then my output is also just another set of real numbers. And what I'm actually doing here is I'm putting in an x value into the function, and while I'm in my function, the function's going to crank out a y value. So I can put a y value here, or I can put f of x. But this is how I would describe the functions that we've studied in the past in terms of this notation. Okay? So for a more recent example now of a function of two variables, we can assume, or we can say that maybe our function f of xy would be x squared plus y squared, for example. Okay, so the idea of a domain and range here will be important, and if we want to specify our range to the image of what's happening in the domain, then we can be more specific as well, and we can see some information for that. Let's take this and carry it on over to the next page and study it a little bit more. So let's take a look at this example, and let's start representing this function in a variety of ways. So symbolically, this is what the function is. Numerically, it means, you know, back in pre-calculus, when you first, even algebra, when you first started to learn about functions, it says that you can put some values in and you get values out, right? So let's try putting some values in and getting values out. How would we put values in? And what kinds of things can we put in if we're going to make some numerical table out of this? So we need a pair of x values, right? So our x values, or x or y values, x and y values. We need a pair of x and y values, and then here's our output. Now I can continue to call it f of xy, but it would be sure convenient if we can assign another variable to this. What variable do you think we can assign to this? Z seems like it's a good idea. So we can say z is equal to f of xy. And then instead of having f of xy here, why don't we just call it z? All right, so we put in some pairs of x and y values. Back in algebra or pre-calculus, we usually like putting 0 in. But we can't just put 1 0 in, right? The x and y have to be certain numbers, so 0 0. And then 1 is the next nice number, 1 1. I guess put negative 1 as well. And as you can see, before we get too far here, we're already listing a lot of different points. So this is probably not the most convenient way to express these numbers. And so we'll find, well, we're going to find that we're not going to be plotting points like what we're doing now so much as to more, we're going to be focused more on looking at the graphs of these things. So anyways, numerically, this is what we would do. We're going to put in 0 for x and 0 for y. 0 squared plus 0 squared is just going to be equal to 0. And then we put 1 in for x and 0 for y. 1 squared plus 0 is 1. 0 squared plus 1 squared is 1. 1 squared plus 1 squared is 2. And then the negatives kind of work the same way. And so we have a set of points that we can look at. Look at the graph. So let's see. Let's see if we can somehow translate these numerical values from a graphical perspective in a graphical perspective. But you realize that we could go out forever and just keep plotting points, right? and you also would quickly realize that this is probably not the best way to go, but at least this is an approach that we can handle. Another perspective to this would be to make a table. And the table, it's kind of tricky sometimes because you need to identify which one's your x and which one's your y, and sometimes it's not very clear. So we can label our x values like this, and maybe instead of starting 0, let's put start at -2, -1, 1, 2. And by making a table, we just plug it into this formula where we have -2 squared plus -2 squared, 4 plus 4, I think that's 8, right? So this might be a little faster than the old-fashioned table that we used to have. X is -1, y is -2, so -1 squared plus -2 squared, what is that, 5? When x is 0, y is -2, we put that into here, we're going to get 4. Does that look okay? All right, and you guys can fill in the rest of the table. I'm going to try to do it quickly, but let's see. Should have done a different function, but this one happens to have nice symmetry. Your table is not always going to look, nice and neat like this, but in this case, this is what we come up with. So these are just putting in values, right? So let's highlight one of them and show exactly in our notes what we were doing. Let's highlight this one maybe. So this one has an x of 2 and a y of -1. So your z value here is going to be, in this case, 2 squared plus -1 squared, which happens to be 5. And that's how we got that number, and then that's how you would find the rest of them. So this is our numerical perspective of these functions. Any questions? All right, now let's see if we can graph this, get a graphical perspective of these functions. And, well, we have the variable x and we have the variable y, and then we just kind of designated f of x, y to equal to z, so now we have the third variable z. So it looks like we should be able to look at this from a graphical point of view. As something that we can describe with x, y, z. And what we could do is we could possibly gather some points depending on which numerical method we're using. Let's say we're using this method over here where we're given the x value. What was x again? X is equal to 2 and y is equal to -1, and so your output, which is our z value, is 5. So it seems kind of natural to say, hey, this is just a point. It has an x is equal to 2, a y of -1, and a z value of 5. So seems like we can express this as a point in the XYZ space. Right? So if you imagine each of these things as being points, each of these things is a point in space that we can plot. So let's see if we can get some sort of picture. 0, 0, 0 seems like it's a nice point to start with. We have 2, -1, 5. So this is a little trickier. 2, -1 goes backwards. 2, -1, and 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That gets a little harder to visualize. So if you try plotting some points around here, it gets a little hard to visualize, and you probably won't get the good shape of this graph until you plot a lot more points in between. We're putting in like 0, 1, 2, 3, 4, but really you're not going to get more out of that unless you start plugging in points like 0.5 and 0.25 and 0.75 and all those other little minor points in between. So I think we're going to have to try to approach this instead of plotting points. We're going to have to try to approach this in a slightly different way to describe this from a graphical point of view. So how are we going to do that? Let's let's rewrite our function z is equal to f of x, y. Okay. So it's too difficult to just plot points unless you have a computer that can plot a whole bunch of points, and then you'll get to see the shape. What? If you want, if you could plot points. Let's see if I have a plotter. A point plotter. What? A plotter of points. A point plotting program. A plot points machine. Maybe I did it in my class back in 2013. I meant to dig this out earlier, but I didn't have a chance. No, I didn't teach 253 4 years ago. What am I going to search for?
Oh, you don't know the name?
I don't know. 2013, 2014, maybe? Did I teach 253? Uh-oh, I have a shot. Do not throw away your shot. What am I looking for? Lecture notes?
No, plot pointer.
Plot pointer? Parameter surface, cross, plot.
You could have just called it plot pointer.
I could have. I think I called it Intro to Multivariable Functions. Let's see if this is it. If it's not, we'll have to move on. Initializing kernels. take that one to initialize kernels. Maybe I should have just went with this lecture. Like I said, I was looking for it and I couldn't find it. Let's plotting functions. So the function that I plotted is this. Should we stick with, let's do the plus one first. Is there something not defined? Yep. What's not defined? Function, f of x. Oh, I need to run that first. There we go. So if we look at it, so this plotter plots just a bunch of points in a rectangular domain in the x and y. So this looks like it might be plotting 1, 2, 3, 4, 5 from -5 or -4 to 4. So if you look at it from the top, you should see those dots like as if they were shadows on the xy plane. But if you look at it from a more pleasing angle, it looks like it's still hard to decipher. So what do you think the shape is going to look like? Let's plot more. So here I have from the top. You can kind of get the shape already. So from the top, I have more points to plot within the 4x4 section, and it's starting to look like a no. Starting to look like a paraboloid. So there's even more over here. So I'm plotting by looking at steps of 0.25. So let's go steps of 0.2, 0.25, 0.1. No, 0, 0 just be, might take too long too. One, come on, 1. So the more points I have, the clearer that this will actually look like. Now really looks like a paraboloid, right? But that you can plot these points, and then we can connect the dots, and then make a nice looking surface graph, which is our eventual goal here. But plotting points is still not the best way to do this, especially by hand. So we have to find other ways to approach the graphical point of view. But let's get this picture in our notes. Let's get a couple of pictures in our notes. So let's I want it on the same page. Are we on the page? Okay, so if you have a computer, yeah. Uh-huh. Oh yeah, yeah. So this just got the idea is that this just got cut off by the domain, which is a square from -4 to 4. So the domain is just a -4 by 4 square, and so these ones in the corner kind of bring you all the way up a little higher than the rest. But if you were to keep going, then those points would even be higher. Yes? Maybe I should have typed this. Computer program can get a nice picture, but it's not practical by hand. So we need a different approach in trying to visualize the graph of this. And to do that, we will, like I said, rewrite our function as a z equals And I don't know if you remember, but we've seen this already. We actually know this surface already. I mean, you guys told me it was a paraboloid because we saw the picture, but you should also be able to tell me it's a paraboloid by looking at this, because this is a quadric section or quadric surface. And do you remember how we approach those quadric surfaces to try to get some idea how they look like? We look at slices and what are they called? Called something. Oh, they're called level curves. Level curves. They're also called something else if you slice it a slightly different way. Anyways, let's go back to the idea of level curves. So if we think about intersecting the surface, whatever this function is, and whatever surface this function generates, if we think about intersecting the surface, I guess they use K or C. If you think about intersecting the surface with a horizontal plane, a plane parallel to the xy plane, then its image, whatever its image, can be reflected down onto the xy plane, and then we get to see how it would look like. So in other words, since we know the shape of the graph already, we'll take advantage of that little piece of knowledge. And we've seen this picture before where we took whatever graph we have and then we cut it with a plane, and then we're going to get an intersection that's going to be a curve. And what we're going to do is we're going to look at that intersection flat on the xy plane. So flat on the xy plane. That image that we get in this particular scenario happens to be a circle. We can be really specific with that. We could say we're going to cut it with the plane z is equal to 1. And then when you put z is equal to 1 into your equation, you're going to get x squared plus y squared is equal to 1, which we know to be the unit circle. We could cut it with z is equal to 2. Then you're going to get a circle of radius. What? No. Square root of 2. Square root of 2 is 1.4-ish. Okay. So what we could do is we can make more cuts. And we can come up with more circles. Well, circles. And what you have here is a set of circles that describe what we call contours. And the contours describe your surface with respect to different heights. And most of the time, the contours are labeled by the height. They don't actually come up with an equation because sometimes you can't describe it using an equation. And so they just label it by a particular height. Have you guys seen a contour map before? Yeah? Yeah, so geography, height map, if you look at a map, yeah, contours. I think I have one. Do I have one here? I have one here. There we go. So here's an example of a contour map. Your surface, you could describe as a function, might be this multi-level terrain, mountain, where you go hiking. And then you can have the contour map describe the height at a particular position. And this would describe a function. So this describes the height. Let's say this is in meters. We got 50 meters is the height. If you had your map out and you had your map have the contour map, and then you find yourself standing over here, you can say that your altitude is about 20 meters up in the air or up on the mountain. So that would be somewhere over here. Let's say you're on that side of the mountain in the trail and you're at 20 meters up in altitude. So you can climb your way to the top of this peak. Uh-oh, too much. By looking at your map and asking yourself which direction should I go to get to the top of the peak. Okay? So this is a contour map. Now, contour maps are not necessarily restricted to just the height. I saw this picture of the United States. Can I blow it up? So this is temperature. So maybe your function is a function of temperature. And what we're seeing here is not necessarily lines. Well, I guess we are seeing some lines, right, for our contour. We're seeing this line over here. We're seeing another line over here, etc. And that describes the contours. And then in the space between the lines, they color it up to say, well, the temperature between here and here is about whatever the temperature is. I can't even see. So this is 100, this is 95. All right, so let's pick, what's this one? About 80-ish. So that yellow, this band over here in our country at this particular projected temperature on June 27th is going to be about 80 degrees around that space. Okay? So that's how we would read a contour map. Now, a lot of programs that can draw things in 3 dimensions or maybe even 2 dimensions can also have contour maps. So if I graph this, it's going to show a picture of that paraboloid, but we can also take a look at the graph as a contour plot. And your contour plot would be, as we saw, would be concentric circles. And sometimes people are a little bit more concerned about not necessarily the contours themselves, but the density, where it's usually defined as the darker ones are lower and then the lighter ones are higher. So in this case, you can see that it's dark in the middle, and as you go outward, your graph gets higher. And so we can think about that as a temperature map, saying the temperature here in the middle is colder, and as you get away from the middle, it gets warmer and warmer. So maybe there's a cold source in the middle that's keeping this cold in our map, and then it gets warmer as you get away from the middle. So there's these contours and density plots that uses color or just uses lines to describe your shape. Frederick?
How far, often how, like the distance between the rings is often significant as well. For example, steepness in height maps, right? Or is that just...
That depends on whoever's drawing the map. So you see some of these maps go by, this goes by 10, the temperatures here go by 5. So you can make, depending on how detailed you want to be, you can go in steps of 2 meters in the height, then you'll have more contours. Or you can go in steps of 20, and then you'll have less contours to describe it.
Right, the rings are closer.
Yeah, so the rings will get closer. So in this particular program, I don't get to control the ring size in this case, like how close the rings are.
No, but the rate
Oh,
changing
yeah. Yeah, so what they do here is that they go in even intervals in the height. So if this is going, the first slice is a little bit past 2, so let's say the first slice is 4, and then the next slice would be 8, and then the next slice would be 16. And then each of those slices, you'll see that it gets closer to each other. So I think that piece of information will be important for us to decipher the idea of the rate of change going in some direction. And we'll study that when we start looking at derivatives. So how close these contours are to each other, also say something about how steep they might be. Yes, that's a good point. Okay. So we could take a look at slices, horizontal slices, and the horizontal slices are called level curves. So that's a level curve. Now, I don't know if I want to go here yet, but let's give this a try. Let's extend our idea to this. What does this mean? And can you give me an example? So my function goes from R3 to R. What does that mean? What kinds of inputs can I put into this function, and what kind of output can I put into this function? So the input now will have three numbers, right? X, Y, and Z would be good candidates. And the output, you only get one number, so a scalar number. We're at the end of the alphabet here, so W. So what we're saying is that W is equal to f of x, y, z is a function. I can't undo now. Is a function that takes in three numbers, three variables, three numbers, and it outputs a single number. And so, can you give me an example of something that would fit this scenario? X squared plus y squared plus z squared. Sounds like it'll work. Right? So that's a function. Now, trying to visualize this is, let's say, impossible. Because let's think about this. The domain itself is in R3, which means your domain is a three-dimensional space. And then now your output is another dimension beyond that. So trying to picture this all together is trying to picture something in four-dimensional space. Can. So the picture of this would be in four dimensions, and unless you're in an altered state of mind, I don't think you can picture this. It's legal now.
Only for one substance.
Okay. Yeah, that's, back in college, you used to try to think really hard, try to picture these things. So, go hang out with a bunch of friends in the quarry, and we talk math and try to picture things in four dimensions. But picturing it isn't the only thing that we want to do, right? We want to see how this would apply to things. So trying to picture this in four dimensions is quite difficult. And so what we could do is maybe we can rely on the idea of a level. The level curve, remember, went from trying to picture something in three dimensions to bringing it back down to two dimensions and bringing it back down to its domain. And domain was in R2. So maybe we could do the same thing over here. Maybe we can picture this And I want to say level curve, but in 3 dimensions, it's probably not going to be a curve anymore. So we can call it level set to be more generic, or since we kind of have an idea that this is probably going to be in 3 dimensions a surface, we can call it level surface. And what we would do is we would imagine letting the output variable, in this case we chose W, we'll let W equal the constants, right? Because that's what we did here. We let the output variable equal to some constants, and then we try to see what the shape might look like. So if we imagine letting the output variable equal to constants, then we might get some idea of how this thing might look like, at least its shadow in space. Oh. So if we say let W equal to -1, -1 equals x squared plus y squared plus z squared. What can you tell me about this? It's what? It's impossible. You got x squared, y squared, z squared. That's guaranteed to be positive. No solutions here. So we can't get a graph out of that. Let's try 0. What is this graph going to look like? It's just going to be a single point. It's possible, but it's only going to work at that single point. Now let's put 1 in. What's x squared plus y squared plus z squared equal to 1 look like? Come on, undo. What's this? No. Sphere, thank you. This is a sphere radius 1. So back to the quadric sections, remember? I said they were kind of important. So, and then let's do one more. X squared plus y squared is equal to, plus z squared is equal to 2 is what? Another sphere radius square root of 2.
So the basic issue is that we have an impossibly inverted sphere at -1. Does it be a sphere with a radius?
No, we don't do inverted spheres.
No, I'm just like it doesn't work because you can't have a negative radius.
Yeah, you can't have a negative radius.
But so it's just kind of this sphere that's going in and out.
Yeah. So essentially, the level surfaces here are going to be spheres, concentric spheres. Instead of concentric circles, or concentric spheres. So the best we could do is picture what happens on the x, y, z space in its domain. And I want to say shadow in quotes because a shadow in 4 dimensions is actually a 3-dimensional surface. Yeah, right. See? Frederick, what are you going to say? Yeah, just like the shadow of a 3-dimensional surface back in 2D is a curve. The shadow of a 4-dimensional surface in 3 dimensions would be a surface. We can represent this as a moving graph by just changing the values of the shadow of K. Okay? Pretty cool, huh? Let's see what I have in my notes. Do I need to talk about more stuff? Yeah, it probably is. All right, we can be done. I need to go to an interview anyways. So your test will probably be graded by next week, and we'll worry about that then.
Can I do this after class tomorrow?